Hello everyone, welcome back to Stewart Technologies. A couple of videos ago I worked on implementing joint interpolated motion. If you watched that video, then you may have noticed there were some slight issues with my implementation.
Flashback.
There are still a few issues with the interpolation, since you may have noticed some joints still arrive at their position a bit faster than the others.
End of flashback.
I've been putting it off for quite a while, but now it's finally time to fix it. And while I'm not 100% certain how I'm going to fix it, I'll take you along on a journey and we'll figure it out together. So without further ado, let's get started. My implementation of joint interpolation was a way to ensure all of the joints of the arm reach their target position simultaneously. I accomplished this somewhat by limiting the speeds of the faster joints such that they all finish at the same time as the slowest joint. While this should have worked in theory, there could have been a handful of reasons why that wasn't the case. After spending some time debugging, I couldn't quite figure out the issue and decided to move on to other parts of the robot. While reorganizing the code, I revisited the controller for the stepper motors, this time properly implementing a PID controller. PID controllers, also known as proportional integral derivative controllers, are a type of control system commonly used to ensure your system or plant reaches a desired set point with an ideal error of 0. The feedback loop for a PID controller looks something like this. The error is defined as the set point minus the measured process variable. The controller takes that error and uses it to produce a control value u of t that directly controls the plant. To tune the PID controller, you adjust the 3 gains of the controller: the proportional gain, integral gain, and derivative gain. Each of these gains have a different effect on the behavior of the controller. I won't go into much more detail about PID controllers since they're a bit outside of the scope of this video, but if you'd like to learn more, you can find a couple of videos on the topic in the description down below. I highly recommend you check out this video by Brian Douglas. He does an excellent job explaining how PID controllers work. After spending quite a bit of time just trying to tune joint 1, I decided to give up on using a proper PID controller for the joints. I spent hours trying to tune this one joint, and even when I thought it was properly tuned, the joint would start to randomly oscillate when left alone for a while. I suspect that the 3D printed structure of my robot has introduced too much slop and backlash into the system, making it much harder to tune the PID controllers as is. This frustrated me beyond comprehension. I had spent so much time trying to tune this one PID controller, and now I'm pretty much back at square one. After some much needed downtime and self-reflection, I finally stumbled onto a solution that might actually work for me. Motion profiles. To put it simply, a motion profile is a plan followed by motors to achieve your desired performance, whether that be a specific velocity, acceleration, travel time, or accuracy. There are several types of commonly used profiles, such as trapezoidal profiles, which look something like this, and S-curve profiles, which look something like this. I'll be trying to implement an S-curve profile since I want the joints of my robot to have smooth motions between target positions. To get a general sense of how to implement the profile, I'll start my work in Python and then gradually move over to Arduino. After a bit of trial and error, I was able to come up with a nice looking S-curve motion profile that gives me the results that I want. To generate the S-curve, I'm using 2 logistic curves with specific parameters to modify the slope of the acceleration and deceleration of the motors. By passing in the desired duration of the move and sample time, I'm able to produce values for position, velocity, and acceleration of the motor during this move. When I attempt to implement this on the Teensy, I'll need to find a different way to generate the profile since I won't have the luxury of the NumPy library. Looking at the generated graphs, we can see that the position graph is basically just a stretched out logistic curve. So theoretically, all I need to do is generate a single logistic curve that takes the motor from one position to another with my desired time or speed constraints. By doing some research, I found an answer on the engineering stack exchange that goes over the equations necessary to do just that. The velocity curve doesn't follow the exact shape I generated in my Python script, but it should work well enough for my needs. Shout out to the Stack Exchange user Barbalot's Dilemma for the explanation. By combining those equations and some of the work I did in my Python script, I was able to write a class called Motion Profile that generates the necessary position and velocity values at a given point in time. It works pretty well, and I'm able to generate profiles prioritizing either time or speed. With a little more work, I was able to combine this with my old joint interpolation code to generate 6 motion profiles that all arrive at their target destinations at the same time. With this promising code, I then began the long process of trying to implement this into my control sketch. But since it's pretty well organized thanks to the work I did last video, it shouldn't take that long, right?
Many hours later.
Oh boy, was I wrong. Not only did it take hours to get the control sketch working again, it still wasn't functioning how I wanted it to at all. As you can see, for certain moves, the arm follows a fairly smooth path, but then for others, it jitters and stutters a lot during movement. I tried implementing accelerations, manually setting the velocities, and letting the Excel stepper library handle both acceleration and velocity, but nothing seemed to work. I suspect it may have something to do with the Excel stepper library and how it handles accelerations, but I ran out of time and couldn't debug it any further because I wanted to get this video out. I may have to write some code to manually control the stepper motors to get the exact results that I want, but that'll take a lot of time to code. So for the meantime, I'll go back to driving the joints at constant speeds without accelerations until I can get this figured out. If you guys have any ideas about how I could fix this issue, please let me know in the comments section down below. Any and all advice is appreciated. Just don't be a jerk about it. I will ignore you. Also, I'm working on a new robot project I think a lot of people might be excited to see. If you have any guesses as to what it might be, drop them in the comment section down below. If you like this video, share it with a friend, and be sure to like, subscribe, and click the bell to receive notifications when the next video drops. Thanks for watching.